How are you doing? Good? Last time I was in that part of the world was almost 12 years ago, so I'm super happy to be there today presenting in Minsk. My name is Lysandre Follet, and I'm the Director of Computational Design within the Innovation Design Studio. And I recently learned that these logograms translate as computer in Chinese. And it actually consists of two characters that literally mean electric brain, which I found was quite beautiful, that concept, which is then translated by Chinese and read as computer. Today we are going to look at the evolving relation between computer and designer within creative practice, or the creative collaboration between an electric brain and organic brain, and what is, when they come together, what can be done in the creative field. But let's step back in history and look at a couple of interesting moments in time. So 1968, Doug Engelbart and the group of 17 researchers was looking at augmenting intelligence, and they built a very interesting system called NLS. That was the first computer system using mouse, hyperlink text, and a lot of those concepts that were kind of completely changing the way people were looking at computer and machine, creating a way to interact with them in a much more meaningful way. This event has been called since then the mother of all demo. And what's interesting to note is at the time, Stanford was also having an emerging artificial intelligence lab, but what Doug group was focusing on was really augmenting intelligence as opposed to creating an artificial intelligence. And Doug Engelbart has a really nice quote in 1962. He said that a tool doesn't just make something easier, it allows for new, previously impossible way of thinking, of living, of being. 1962. In 1997, after a few years of research and development, IBM built Deep Blue, a state-of-the-art computer designed to run powerful algorithms to play chess against the best player in the world. May 11, 1997, Deep Blue is set for an historic chess game with legendary chess player Garry Kasparov. We all remember what happened that day. Deep Blue beat the world chess champion after a 6-game match. 2 wins for IBM, 1 for the champion. And at that time, it's really the first time that people start to realize that an algorithm can not only do mundane mathematical heavy loading day-to-day tasks, but also start to tackle some things that before we thought only human could do. What is less known is that following his defeat against Deep Blue, Garry Kasparov recognized the potential of such an advanced computer system, not just as a human versus computer setup, but as a partner in the game. Garry Kasparov developed a variant of chess called advanced chess, also sometimes referred as center chess, which is quite a beautiful image, with the objective of a human player on a computer chess program playing as a team, not competing. Many advanced chess players have stressed the fact that playing as a team with a computer has merit in increasing the level of play to heights never before seen in chess, producing blunder-free game with the qualities and the beauties of both perfect tactical play and highly meaningful strategic plans. He also gives the viewing audience an insight into the thought process of strong human chess player and strong computer, and the combination. So that notion of algorithm, which at the time was very new, has since then kind of started to evolve. And one of the other key moments we need to recognize is Google. You can note that the page hasn't changed much in almost a decade. And this is same year as Garry Kasparov come up with this system. A couple of bright minds from Stanford launched Google. And it's a simple idea. It's basically just indexing web pages with a ranking algorithm. And at that time, 99, the Observer talked about complicated mathematical analysis, and John Norton write about an ingenious algorithm. Since then, we can see on Google search timeline that algorithms have evolved a lot. There is a lot of intelligent features that keep being added over the years. And Google products are becoming more and more personal, capable of cross-referencing thousands of data points and giving you a fully personalized search experience and well beyond, as we all know today. Of course, in today's world, algorithm and artificial intelligence are everywhere, even in your pocket. It's driving your car. And I really like this example. If it's playing, let's see. Yeah, it's not playing. It's a bummer. It's a cool video. But I like it because you kind of see how the vision system works, and it kind of gives you under the hood kind of perception of what's going on there, with the vision recognizing the other car, the road, the traffic. So like never before, our digital and physical world are really becoming linked, and it's transforming how we make and interact with things. So what I'm interested to talk about today is how we can leverage those same powerful concepts and methods to radically change the way we create products, and how those products are becoming more and more personalized. So at Nike, from the beginning, we've been maker, craftsman, thinker, and innovator. It's a mindset that really helps us push the boundary of the possible and change the landscape of modern sport design. If we go back in 1950s, this is Bill Bowerman. It's a veteran track and field coach, and he's also one of the co-founders of Nike. And that coach was really dissatisfied with all the available products. They were constructed of weighty leather and metal, and as a result, he became obsessed with trying to improve those products, shaving ounce of shoe to help runners slash second of their best time. His quest wound up redefining athletic footwear. In 1980s, we can see Bowerman in his laboratory custom fit shoe to his runner needs. So he will take his runner, have them stand on a piece of paper and draw the outline of their feet. He will note the width, their ankle, their arch, and he will start to customize the shoe by hand. So a very analog process, taking an existing shoe and cobbling it, shaving it, extending it, and so on. Nike mission statement and vision is to bring inspiration and innovation to every athlete in the world, not only for professional athletes, but all athletes, athlete asterisk. And as Coach Bowerman said, if you have a body, you're an athlete. So it doesn't matter if you're running like the fastest time in the world. If you're just walking to work, that's an athlete for us. So we can ask ourselves, but how do we design for every athlete in the world? Well, it's complicated. Because the reality is we all have a different body. We're dealing with a really complex problem here because we can't possibly by hand design a different product for every single person in the world. That is not something we can do. And for most of the people, the left and the right foot is even different, sometimes up to half or a full size. And I love this illustration that shows how the body is throughout different sports. Those are all professional athletes, and they really show the diversity and the beauty of the human body. And what we've done for the last few decades is, as we design products, is we optimize against what we call sample size. So sample size is often men's 10 and women's 8. And then we will take that model and scale it up and down. So just think about it. If you take a chair and scale it up, you probably end up with things that are over-designed. If you scale it down, it will be too fragile and probably break. We had the exact same issue. Performance isn't perfected. With traditional method, it is as good as it can get. And it's that idea of designing for average. So again, we cannot design for every single person. So we take a sample size, and then we extrapolate for the average athlete. So how do we go from designing for average to making a batch of one? So a personalized product. So in 2013, we started working with Jamaican Shelly-Ann Fraser-Price sprinter. She's the world's fastest female athlete, high-cadence power sprinter, with the goal to build for her the best performance spike ever for the 2016 Rio Olympic Games. Shelly-Ann is an interesting case study because she actually wears size 5 footwear, so very small feet. which we knew we always had issue with because it was at the bottom of that sort of scaling process. So the shoe will be over stiff and will often create injury throughout the training, which will remove the capacity to compete. So great subject for our project. What we do really well at Nike is we spend a considerable amount of time to meet with athletes. We put them at the center of the design process. And using state-of-the-art equipment, we have taken the data from thousands of athletes in the world. From the best marathon runner in the world to someone that just started running or walking. And I'm going to show you a sneak peek at how the sports science team do it back in Portland.
If you take science and design by themselves, they have no power. They're not going to do beautiful things, but the overlap and the convergence of those two together, it's when beautiful things happen. It's an extremely creative process to be a researcher in the Nike Sport Research Lab. If you look at all of us, we're all extremely passionate about sport. We geek out on the science of athletes and athletic performance. Every day is a new challenge, and we want to make athletes better all the time. Athletes ask us for three things. They ask us to make me better, to protect me, and to inform me. The better you understand the needs of that athlete, the better you're going to make product. Motion capture is one of the tools we use. What it allows us to do is really objectively understand an athlete in motion. We use high-speed video. Most digital cameras capture around 30 frames a second. We can do 30,000 frames a second, so we can see things you don't necessarily see with the naked eye. Our force plates take thousands of measurements per second, and we get forces in three-dimensional space. We have environmental chambers. We can collect things like expired gases, so we know the amount of energy your body is using to do a particular movement. And in these chambers, we can accurately replicate weather from anywhere on the planet and make sure that our product is going to work in those environments.
Okay, so how do we best leverage data to inform design? Well, it's an interesting question because we have all that richness of data, but with traditional design method, it starts to make sense of it. And the reason is that most of the creative software of the last decade have been replicating traditional processing, giving the experience of drafting, drawing, or sculpting. They translate how humans have traditionally been working with physical material or medium, and there is a little bit of a loss in translation, a lot of interpretation in that process. And this is often what we refer as CAD in the old term, which is computer-aided design. So that idea that it's mainly used to increase the productivity of the designer, which is interesting, but it doesn't really empower the designer to unlock imagination or spark creativity. So in early 2012, we started looking at a process called computational design. And I always like to go back to the definition of Wikipedia. Computational design is the application of computational strategy to the design process. So remember that idea of algorithm. The goal isn't to document the final result necessarily, but rather all the steps required to create the results. Which is very interesting. We're not going to design one object. We're designing the process to create all the possible solutions. In computational design, we often found three main ingredients: a design scheme, a means of creating variation, and a means of selecting desirable outcome. And computational design have been heavily used by architects in the last 15 years with pioneers such as Zaha Hadid, and it's now transforming pretty much every industry because it's applicable to a wide variety of fields. So the first step that we went through is data collection. So we brought back Shelly-Ann Fraser-Price in our lab. She's equipped with motion capture, so we can capture three-dimensional data of her running. You can also see on the left the force plate and the opto-jump, so we can know exactly every stride that she applied. And by placing sensor in the shoe, we were able to track how much forces Shelly-Ann applied on every single stride. Once the researcher finished to analyze the data, we started to have a good understanding of what needed to be achieved to hit performance target. We needed to be able to create a tunable sprint plate structure that will be as light as possible while maintaining an accurate control on localized stiffness. And I want to pause there, localized stiffness, very important, where before we had the same stiffness for every single individual. The second step, which is a very important step in a computational design process, is to translate the design problem into constraint in the generative objective, or computable parameters. And for that, we look at nature to find guidance and inspiration. A lot of the systems in nature have been evolving over thousands of years and have found very performing solutions for what they're trying to solve. So this photosynthesizer, planktonic diatoms, is a microscopic organism, and he solves this problem really well. He's very light, but has a very stiff shell. So he can travel with very little energy, but he never kind of dies. And that's the beauty of nature, because if a system is not performing for his environment, he either has to mutate, or he often disappears and kind of move on to something else. Or if the environment changes, the system again mutates and adapts. So this organism, of course, has evolved over millions of years, and it has become the most productive group of phytoplankton. The idea here is not to look at this like a pretty picture and say, oh, this is beautiful, let's just make something that looks like this. It's actually looking at the principle of the architecture of that organism. And that's how we started to shape the design process, by writing algorithms that describe how the design gets constructed. And it's really that beautiful idea from Dog, which is building a tool versus using a tool. So we are translating design idea into computable parameters. And as Dog said in 1962, a tool that doesn't just make something easier, it allows for new, previously impossible way of thinking, of living, of being. Step 3, which is maybe the most exciting for creative people, is creating variation, generating design solution. So once we have a system in place, we can quickly generate massive amount of design. We can experiment with parameter, make adjustment to the algorithm, and introduce constraint. The designer and the algorithm work together to translate this understanding to create something extraordinary, a design never before seen with a mathematical simplicity beyond human comprehension. This fluid geometry unlocks a fascinating kind of living intelligence, one that treats that structure and pattern as data, but not in a static spreadsheet, in an active ecosystem, as you can see here. Translated into a variable stiffness, three-dimensional structure, similar to the one found on the beautiful diatoms. This structure can provide more support, where more support is needed for each individual, highly tunable ground contact traction, and an optimized weight to stiffness ratio. So maybe the most exciting step for me is exploring design space. So we now have that sort of living ecosystem, and computational design offers a very different approach. We are leveraging dynamic systems that we can interact with, changing parameters. Instead of creating one static design, we build a dynamic system. Each time we run a loop, we generate thousands of solutions, building a design solution space, which is actually a non-finite space, that there is no end to that space. We shape the design process itself. This is a very cool video. This needs to work. Okay, let's see. Sorry about that. Yeah, perfect. So this is a design space exploration for a drone chassis by software company Autodesk. And as you can see, multiple design solutions are explored by the computer and optimized to find the best solution to the given design problem. Endless possibility, unlocking imagination. What's interesting there is, as you can see, there is a lot of ridiculous solutions that make no sense, that don't work. But those are the creative artifacts that in that new process really kind of spark the creativity and the curiosity of the designer, because you get a lot of solutions that you will have never envisioned on your own. So this is great, but you have to deal with a huge solution space. So how do we search that design space? We use a couple of methods. The first one is computer simulation. We don't want to be the human looking at thousands and thousands of solutions and figuring out if they make any sense. So we actually ask the computer to run a couple of tests that replicate what is happening to the physical product in real life. And we start to understand where yield happen or fracture happen. And the computer is capable of narrowing down that search on that solution space by giving us a bucket of solutions that are all viable products in terms of performance. So we quickly understand our design space, and we narrow down the search space, and remove all the solutions that will not meet our criteria. And then, leveraging additive manufacturing or 3D printing, we can drastically cut development time and produce highly tunable performance footwear to test in the real world, which is always what we do. Like, we always want to test it on real athletes to get also perception feedback as well as performance feedback. So again, cutting the development time, because what we used to do is send a CAD to Asia, open a mold, and it will take almost 3 months to get one design. That is that average design. Where now, overnight, we can 3D print a plate and put them on the athlete feed the day after. So we are entering that beautiful feedback loop where we make a product that is generated by the algorithm, we test it, get new data, and feedback that data into the algorithm to create the next generation or mutation. So this is the first 3D printed prototype ever grown and assembled in Portland overnight. And in a matter of days, we were able to go through hundreds of revisions of the same design, where before it would have taken, again, a couple of months to just get one. We tested on athlete feed, gather new data points, feed them back. Highly iterative design process. And then we get to be the human in the loop, and our role becomes more a role of curation and curator. At this stage, it's to reframe subjective human preferences, such as comfort, performance criteria, combined with aesthetic. I like this one, but this one doesn't work. This one is way too ugly or bulky, but it performs well. We get to kind of curate that solution space. And augmented by the computer, the designer takes that role of curation, evaluating and selecting the output. And this is where we landed for the Rio Olympics, taking also cue on the coloration of the beautiful system found in nature. And then we're going to move on the exciting part. So with computational design, we have solved one of our most challenging design problems. Remember, I told you we used to design for size 10 and then scale up and down, scaling performance as we go. So if we look at that slide, we have 4 professional athletes. They all run the same distance, which is 100-meter sprint. However, what's interesting is they all have different foot size, going from 12.5 to 5. And again, we used to design for size 10, so the 12.5 will be like almost like a noodle, way too soft, and the small size will be way too stiff, out of spec. This time around, we went back to the algorithm, and we actually rerun performance targets that were true to each size. And we were able to generate that beautiful family. And as you can see, if you start to play that game of finding differences, you can see that the network slightly adapts. And of course, from far, they look like a family. It's that idea of DNA. They all share the same code, but they have slight mutations that are very specific to the performance target we're trying to hit. So a step closer to personalized product. And then we decided that we wouldn't stop there, because there is something beautiful that is happening in a stadium, is that as you go from 100 meter to running around the track, there is some new constraint and new design paradigm that are happening. You're starting to run in the curve as opposed to running straight. So why not look at that and ask the algorithm, can we also solve for this? So again, a little bit of a case study. So those are 4 professional athletes. On the far left, you have Shelley and Fraser Price that run for less than 10 second power sprint straight line, all the way down to Mo Farah, which is a distance sprinter that run up to 5K marathon runner. And then, of course, again, beautiful design test case, you have all the distance in between. So as you go from running a straight line to taking the curve, again, the geometry gets tuned specifically to start to allow for medial flexion. For the 10K, it gets as minimal as it can based on the data, providing traction and stiffness just where you need, as you can see on the right. And this happened after 3 years of hard work. We could have not dreamed of a better stage than Rio Olympic to validate. Let's see. Sorry about that. I don't know what's going on with that. Yeah, perfect. Validate on the track the performance of our product on the feet of most of the athletes in the world, helping them achieve their dream. We had more than 45 medals in those new products, which we had never done before. And finally, we thought, wait a minute, at Nike we don't do only running, we also have different categories on sports, such as American football or football, that often try to solve for the same problem. If you think about soccer or football, you kind of want to also play with the same constraint of stiffness versus weight, being able to cut, to decouple in an agile way. So this is actually American football. We rerun the algorithm with different performance targets to land on a unique design. And then baseball also. So what we have done here is really to create a family of performance products that all share the same DNA, that idea of DNA that we all have in all the organisms, the algorithm, that same algorithm with mutation to generate a wide array of highly performing products. In this creative process, the computer generates thousands of design solutions that the designer on its own would have never envisioned, as well as many creative artifacts like we've seen. Imagination is truly unlocked with surprise and delight. The computer becomes a partner in creation. It's that very same beautiful idea that Garry Kasparov had at the time, using the computer as a partner in the team, as a team, not trying to compete with the computer, playing as a team. What we're doing here is really augmenting creativity. And machine and system are becoming more and more intelligent. There is a beautiful learning opportunity for the design and creative process. Today, I want to finish on a quote from Lysandre, and you must be familiar who he is. He's the Go player that got defeated by AlphaGo. And he says, AlphaGo showed us that moves humans may have thought are creative were actually conventional. I think this will bring a new paradigm to Go. Thank you very much.